Anyway.
Hang on. Are we live or?
Well, on stream, not yet. We don't do the introduction yet. But
Right. We should have intro music.
Yeah, we should. But
I got that covered. Hold on, let me pull that up.
Metadata, it's all right.
Hold on.
Connect,
here we go. Okay, radio music is playing. Da da
da
da da da da da da. Da 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 da.
We're live. Hello, everyone. Sorry for that. We just had a little crash on the radio broadcasting side end side of things. Blah. Welcome to Dangerous Cosmology. After 2 weeks of not doing the show, we are finally back with Dr. Sarah Bosman. She's back from her holiday and recovered from her illness. Say hello to everyone.
Hello.
And also there's you heard Selfish Spy is also with us tonight, as always, and we've got Chank doing the video stream. Yeah.
Let me hold on.
We don't have Nightfall Zero with us tonight because he's not feeling well. So
sorry about that.
The show to us.
I just transferred audio to my headphones because it was coming through really loud on my speakers, and I didn't want a weird pickup. But it should be good on the it should be good on the video end now. We're set.
Okay. All right, Nightfall isn't with us because he's not feeling well, but still, we've got a show for you tonight, and we intend to make good for what we missed out on. Tonight's topic will be stars, all about stars. What are stars? Why are they? And how did they come into being? Yes, we've got quite a lot of questions, and even though Chank said he would be quiet all over the stream, I humbly asked him to support us with asking things because I'm not the best at talking, and
he wants me to ask stuff because I'm stupid and I ask dumb questions.
Well, no, see, that's
no such thing.
That's the thing. That's the thing. Everything that people think is a stupid question is secretly
there are no stupid questions.
Absolutely.
I can't remember
only
what I was
stupid
gonna
answers,
say.
And we won't have any of those tonight. So,
no.
to get started,
not unless I start speaking.
My first question in the channel was what are stars and why, but that was a troll question. So, we'll start from the top. Oh,
well, actually, that's not a troll question. That is good. That is a good foundation. What defines a star?
Michael,
what is a star? What defines a star? Is it luminosity?
No,
is it mass?
Is
it gravitation? Like what defines a star in the science of cosmology? What is a star? That's a brilliant question, honestly.
Yeah, no, it is. Thanks. It's actually a lot less easy to answer than you may think. I think what defines a star is that it is a bunch of gas which is capable of producing energy via fusion. That is the usual definition of a star. Now, once you get to the edges of exactly how much fusion do you need to qualify, or what happens when you stop being able to have fusion, do you keep being a star, the kind of edge cases get really fuzzy. I think we had quite a few questions about exactly the boundaries of what is and isn't a star.
Oh yeah, I literally asked 2 weeks ago. I posted a video. Anton Petrov made a YouTube video about how brown dwarfs may not technically be stars, and I literally posted in Dangerous Cosmology. I posted in Dangerous Cosmology. I was like, I demand an explanation. What is this?
Yeah, no, absolutely. Because the question is like, how much fusion do you need in your core to qualify? Like, is it enough to fuse one atom at the start of your life if you're a small star, and then never fuse anything ever again for billions of years? Do you still qualify just because you did one of the events? Like, that's the kind of territory that we get into. Like, exactly how much, and we don't really know like exactly where the boundary is.
So one might argue that, ironically, star was a nebulous term.
Nice pun.
Yeah.
I think no one really worried.
Yeah,
about
you got me here. So the dad jokes are gonna fly.
Oh yes, I love puns.
Okay. So I was intending to go through the questions from the top, but maybe we should go through them in order of a relation, so they all line up nicely.
Yeah.
I have the question. I would like to know if and how planets, if enough mass is added, turn into stars. And Nagi added the question to that. What's actually the matter with brown dwarfs? Actual stars or hot gas giants? Where do we draw the border?
Yep. So those are exactly related. So basically, when you get a bunch of gas together and you let it collapse just because gravity exists, about 90% of it will end up in normal stars, stars that we call main sequence stars, the ones that are just named by a letter in elite. So from A, B, O, and then all the way to M, and so on until it gets fuzzy for the really, really small ones.
So
Now,
how do you list those? Because there are two ways, and there's one way that's accurate, and there's one way that pisses off astronomers. So as a cosmologist, how do you list them?
as a cosmologist, I only ever see OB stars. So they're the only ones I'm ever concerned
All
with.
right,
Everything
so
smaller than that, I'm never gonna deal with.
OBAFG, OBAFG, KM. Yeah, OB a fine girl kiss me.
Yes.
You not KGB foam. Which I've seen.
Well, that's
I've seen people genuinely get upset at KGB foam, and they're like, "That's not right."
well, I use it as a mnemonic device in Elite actually for what I can fuel from. To
Yes!
me, it's fog kabam. Because like if there's fog, it goes boom. So it's fog kabam. That's how I remember the ones I can fuel from.
Oh, not bad. A new one. Fuck kabam.
So because basically beyond M to the really small stars, you have things like L and T and Y, which are the fuzzy cases that you definitely couldn't fuel from. Definitely not in Elite. So they're special.
Yeah, but in Elite it's more easy than that, because if you go in the filter list and just check the top 7 stars from the list, those are the 7.
Yeah,
that you
pretty
need.
much.
Okay, but back to the question: where do we draw the border between planets and stars? If
Right. So these 90% of all stars all have basically the same internal structure. They're different sizes, but they're basically just scaled versions of each other. They have one template, and you scale it all the way from M to O. Basically, they have a core that is fusing hydrogen, so combining atoms of hydrogen, which have a core, which is a proton and one electron going around it, and getting them pressed together enough so that they fuse and become helium. And that's their main source of power for most of their life, at least 95% of their life. That's all that they do. All the other types of stars we see, all the bright ones like Wolf-Rayet stars and the ones we'll talk about later, they're basically exceptions and what happens when you can't do this anymore, when you can't do this normal process, which is 90% of all stars. Now the problem is, where's the limit for when with this internal structure that they all have the same of stops working on the small end? The pressure you need to combine these atoms efficiently to even get the reaction to happen at all, and get the structure of a core in the center surrounded by the rest of the gas, is at about 100 Jupiter masses. So if you're at about bigger than 100 Jupiter masses, you can quite confidently say there is enough fusion going on in the center that you're slightly bright and you have the basic structure in place. Now you go below that and things get a lot more complicated, because hydrogen fusion might not work. You might have to rely on other more easy to achieve fusion mechanisms. And that's where you get all the complications.
I thought the easiest fusion mechanism was hydrogen to helium.
There are more obscure ones. So if you can't, the thing is, hydrogen fusion will happen the first if it's possible, just because stars contain mostly hydrogen. So if you have enough pressure, it's the first thing that will happen if it can. If it can't, then the hydrogen will just sit there, it doesn't do anything. and slightly heavier atoms can then fall to the center of the hydrogen. And then those slightly heavier atoms can do more exotic things in the center. So the two ones that people talk about the most are lithium fusion and deuterium fusion, and those are a bit more theoretical because they're more complicated than just hydrogen. But we think from theory that the easiest fusion you can get is actually lithium fusion, and that can happen even if you're only 15 Jupiter masses, more or less. That would be enough pressure to at least make some lithium atoms fuse into complicated byproducts. So then you really have the definition problem, right? Because if you only do so little fusion, the chances are the light you make will not even reach the surface of the star. So it will still look like a brown dwarf, and you won't see what's going on in the center. So, how would you even know? It's not that easy.
So
it does sound as if we need to make a distinction there as well.
Hold on, sorry, I don't mean to interrupt, but can we back up just a little bit and get a basis? Can we start at a point and say, what are the stars that we know? What are their classifications? And then what defines them? So, like, what is "Oh, be a fine girl, kiss me"? What do these star names mean? At the I want to bring it all the way back, like most basic, like Cosmology 101. What do these star names mean, and how have we classified them? Can we start with that?
So, yeah, it's just temperature. So it's just a measure of how hot they are. That's it. So they go from O to M, and that's the order of the most hot to the least hot. Like, pretty much that's just it.
So it's not luminosity, it's temperature.
It's actually based on temperature because that's what was measured about them first. We couldn't see their sizes because they're so far away. We couldn't see pretty much anything about them other than the type of light, and the type of light gives you the temperature.
Now, you see, I was told that it was peak wavelength that the spectral class was dependent on.
Yeah, absolutely.
No, that's what you're talking
actually
about
the
then,
same.
yeah. Yeah.
It's actually the same. So if you have a bunch of matter and you heat it up, it emits light in what is called a blackbody spectrum. That just means it emits all types of light, but it has one preferred wavelength. So our sun, for example, has a preferred wavelength or a preferred color, which is slightly yellow. Like, not dramatically so. It's like mostly white, not really yellow, mostly white. Then as you go more and more hotter stars, they have a preferred peak wavelength, which corresponds to their temperature, which is more and more blue. So the more blue you are, the more hot you are, because that's the most simple kind of light emission you get just by heating stuff up. You emit all colors, but with one preferred wavelength in a power law distribution.
I don't want to be an ass. Actually, yeah, I don't want to be an ass, so I'm not gonna say it.
I'll be an ass. My question is then, if I think you're thinking in the same vein as I am, how do we have Betelgeuse? How do we have something is a yellow or a red star, but it still has a high luminosity versus its actual heat?
Yeah, definitely. So I think Betelgeuse is actually an O-type. I think it's not even... actually, I'm not sure. I'm actually going to look this up. What's the type of Betelgeuse?
Betelgeuse is... Oh, be a fine girl, kiss me. I think it's definitely not an M because it's a supergiant.
It's a supergiant, right. So remember what I said about that's what 90% of stars do when they form, and the rest is an exception. So supergiant stars and giant stars are the exception. They're what happens the rest of the time when you can't do this normal mainstream process of fusing hydrogen to helium. In the case of giants, it's because they've run out of hydrogen. They don't have any more. So they have to start doing more exotic stuff. So they leave this main sequence this like main category of stars, and they do something different.
Hmm. They fuse helium.
Yeah, they fuse helium, and then after that, they fuse more and more difficult to fuse stuff, all
Uh-huh.
the way to carbon until they get to iron. When they reach iron,
Yes.
they're basically fucked because iron cannot be
Yeah.
fused. You don't gain any energy by fusing iron, and
Yeah,
that's when stars
iron.
die.
But what would you
Iron-
get if you fused iron?
Well, they do because they can't stop it from happening. But fusing iron doesn't help you resist collapse, right?
Oh, okay.
Yeah.
The reason stars do fusion is because the atoms are forced together, but the fusion actually gives them a lot of heat that pushes them back out. So it's a big balance of collapsing in, being pushed out by the heat that it's making. But when you
So
get to iron, you don't get a pushback. You just all falls in with no way to stop it.
yeah, in Elite, Betelgeuse is a red supergiant, which would put it in like K class maybe.
Let me get a.
Well,
But-
spectral
It's not the
class,
main
it should be
sequence.
M1-2, 1A-1AB. That's the official spectral class of Betelgeuse, or Alpha Orionis.
Yeah, except the main class is in that case a giant because it stopped being on the main sequence by that point.
Yeah. Well, it's.
I'm gonna get a Hertzsprung
Nice.
Russell diagram up just now. Just
I'm ashamed to use Wikipedia for this stuff, but when I use it, I should actually use it in English.
Well,
Yeah,
it's just that if you've ever been to Betelgeuse, yeah, it looks like Sol. It looks like the sun, except it's really, really, really freaking huge. And how accurate is that to
So-
the actual, like what we actually expected to be like in the real world? Shall we say? I'm sorry
No,
for my
it's
I'm sorry for
actually
my
quite
voice. I'm
accurate,
kind of
you know.
sick. I have a cold. Sorry.
No, I want to explain something first because I see this being brought up in the chat too. So why is Betelgeuse called an M class? Well, it's because of what we define the letters as. If you remember, it's just based on temperature. And an M class is actually quite cold. So why is Betelgeuse quite cold? That's why it's technically classified as an M class, is because the surface of it is actually quite cold, even though it's so big. And that's because when it's run out of fuel in the center, it started pushing its outer layers out because the outer layers have become useless and they don't get to collapse anymore. They get a pushback effect when the core starts collapsing. So the star expands, becomes a giant, and the layer that you see is actually not entirely connected to the core anymore. It's like a sort of puffed up envelope of the core that is now doing carbon fusion or whatever it's doing by now. So the actual outer surface that you see is quite cold because you don't see the core that is busy doing all this exotic fusion. So actually, when a star dies and becomes a giant, the processes in the center become a lot more extreme, but the surface looks like it's cooling down because it's expanding. And that's why it's classified as an M based on the temperature that we see. Although it's not a main sequence star, it's a dying star. It's a giant star.
So it's
it's
close to its supernova.
it's
nova
on the
phase.
it's on what you're saying is it's on the verge of being a
Boom.
would it be
Yeah,
an S
it's
or
on its way
a
to-
carbon star maybe?
By the end, it can vary. There's many factors that affect what you end up as. It's quite complicated, actually, but it's on its way to dying and not having any fusion anymore.
I think.
Oh, you do?
think we've. Yes, I do think. You know, that's. I'm gonna stop with that joke so that I can get on with my point. I think we have sort of skipped over something just a bit that may be leaving people confused, and that is how stars actually work, what functions. So, would you guys mind if I just give a quick explanation of like the functions that go on within a star, so that we can hopefully understand the rest of this?
Sure, why not?
Okay.
Yeah, go on.
Your
Shoba, are you
wings
cool with
are-
this?
Yeah, go on.
Okay. Now, you see, this is the challenge that I haven't had to do this for 6 months, so here we go. Right. So, as we have already covered, hydrogen fusion is what powers most stars. No, I'm gonna try again, that was a poor beginning. I've immediately failed. Right. So, we know that hydrogen fusion is what keeps stars going for the majority of their life. That's when one hydrogen atom joins with another.
Make a baby.
In essence, they make a baby, and they make not another hydrogen, a helium. Well, technically they can do another hydrogen, but that's more advanced stuff. In essence, what they do is they just come together, they kiss, they fuse, become helium, boom boom, you've got helium, right? Now, if you don't have enough hydrogen to keep going at that hydrogen fusion, then eventually you're going to need to use up helium. Now, one thing about hydrogen fusion is that it gives off energy, right? We know this because we can see it in the sun. It's given off not mainly as light, but we see a lot of it as light. And so, another thing about that energy is that energy goes into keeping the star stable. That's what Shoba was talking about with with the fusion itself being the source of energy that stops the star from collapsing. Fusion is forcing itself out. It's called a radiative zone where that happens. That's what forces it out. Now, hydrogen fusion gives off a lot of that, and it also requires a lot of energy to start. However, when you run out of hydrogen fusion and you go on to helium fusion requires a large temperature to start, which depends a large temperature to start properly and sustainably. And so ultimately what that is dependent on is how much hydrogen you had and the rate at which that was fusing, because that would determine how much heat you have left over to then allow the helium to fuse. That's essentially the difference between a high and a low mass star. But let's go down the high mass and pretend that you've got a large enough energy to start helium fusion sufficiently. And so what ends up happening is that this helium fusion, once it starts, it's a completely different ballgame. Yes, it does give off energy in the form of light, but it also gives off a different push. It gives off a much larger push, and so what happens is that during helium fusion, during this stage, the helium forces the star to expand to what we're talking about now, a red supergiant. Now, if it was an O class star or a B class star, aka it had a very high mass and so it was giving off a lot of energy, and a lot of energy means like a high wavelength, and it was like possibly even blue. Those blue small stars, and I don't mean small as in like low mass, I mean small as in like relatively small as in volume. Once these things start helium fusion, they expand so greatly that the fusion ends up slowing down simply because of the amount of space that is allowed to happen because of that. And so, what ends up happening is there's a small decrease in the actual rate of fusion, and that ends up reducing the amount of energy that you get, and so that causes the star to appear to cool down on the outside. That is what changes its spectral class. Now, eventually, because it's slowed down but it's already expanded, this expansion will stop and it will actually collapse back slightly. But it will be at a different volume than it originally was, because now helium fusion, it's fighting against gravity, and that's in a different stage of equilibrium. And so essentially, as you start to go down this chain of fusions of different elements, helium fuses into, I think, what is it? Helium fusion, carbon,
Then oxygen,
helium
neon,
fusion,
magnesium,
carbon,
silicon, and iron.
all the way down. Now, in each of these stages, the energy that is given off is different, and so you get a different expansions and contractions and all of that. But once you get to iron, as we've said, that is the killer stage for a star, because iron is very funny in that it actually doesn't give enough energy to do that pushing motion. And so when you get to iron, it actually takes in more energy than it gives off. And so once you're at iron and iron fusion starts, it's like what's a good analogy? Anyone got a good analogy for finishing something very, very exponentially quickly? Anyone? It's like me it's like me and a group of friends realizing there's only one brownie left and we all go for it. That is how quickly this iron fusion sucks in the energy. Now this causes a huge instability because now you've not only got no pressure from fusion, you've also got nothing to push against the force of gravity, and that's where you get the collapse. And this stage is also based, and essentially this stage is where you either get it collapsing so much that it becomes a black hole or a neutron star, and that is also based on the mass. And so ultimately a star's life is entirely based off of these different masses and different contractions, entirely based off of the energy that is given off. And so that wasn't as quick as I'd liked it to, but hopefully now we all have a better understanding of what everything we have that's been talked about, and so hopefully that's helped everybody.
Your verdict, Sarah?
Yeah, that was very good. Very good
Thank you.
summary. Yeah.
What
Was there anything
It's
wrong
true
with
that
it?
A plus?
it's true
No.
that it's an A. Some of my first year uni students are worse than you. Actually, most of them are. You wouldn't believe how bad they are at the HR diagram. Anyway,
That's something. That's
Well, I mean,
actually-
technically, I've been doing first year for the past year anyway, because advanced higher in Scotland is actually the level of a uni course, and that's why if you get all A's in your advanced hires, you can actually skip a year in uni. But that's a
Fair
different
enough.
topic. Sorry, so
So what
it's true that
what I'm hearing
so
is that basically stars eat and shit out and eat and shit out, and once they shit out iron, that's pretty much the end of them existing because they can't eat iron to shit out anything
They-
different.
and
They can
and your
eat-
analogy
they can eat
analogy.
it, but it
Sorry,
doesn't
I'm
help
gonna-
them. It doesn't give them any energy. They can eat it, but it doesn't help them live. It's like eating wood, right?
Uh-huh.
It doesn't help them. They
And
still
I'm
will
go-
because they have no choice. But
I got to simplify shit for myself because I'm a dumb redneck and I don't understand anything. So
I'm just gonna go with your analogy. If you were to, well, I'm in my parents' house, so I can't exactly be quite vulgar, despite the fact that I'm Scottish and it's in my blood. But anyway, going through your analogy, if you were to poop out iron, in this analogy, you would be Elvis Presley. The star would be Elvis Presley.
okay,
if you were pooping out
so
iron.
when
If
you,
you-
when
if
when
you
you're
get- if you sort of
when you're pooping out iron, you're Elvis Presley or Johnny Cash. You are the king.
yes, I don't. Well, actually, I don't know about Johnny Cash. I liked his music, but
Oh god. Will you get
Okay.
back on topic?
yes, I think that would be quite useful.
if there was anything I could add to your summary, is that it's true we think of stars at the end of their life, so the really big ones, when they run out of hydrogen fusion. It's true we think of them as going through these phases: hydrogen, then helium, then carbon, and so on, as if it was like a clean transition every time. But it's actually they kind of happen at the same time. So, for example, in big stars but not too big, like the B types, you get all these layers. So the central layers could be currently eating carbon into magnesium, and then a larger layer higher up might be currently doing the same with some leftover helium. And then all of these elements can kind of mix and it becomes a big, big mess.
So you can't really tell what's happening at which stage.
It's extremely hard to tell, especially from the outside. From the outside, you have no idea what is currently going on in the center because there's all this mixing, different layers, many things going off at the same time.
So how do we know that's happening actually?
Usually we don't. So when you enter the very last phase, this carbon to magnesium to iron, once you start producing iron and you get an iron core, you only have a few thousand years, maybe even hundreds of years to live. But from the outside, you can't tell that that point has been reached. So basically, stars like Betelgeuse could have reached that point, and it could explode literally tomorrow, and it wouldn't be that surprising. We
Well,
can't really tell how long is left.
That would be a sight to see. Well,
What
how far it
about-
is away, we wouldn't know for another dozen years or so.
Yeah, right. We'd get the information that this happens now. It might have happened by now when we don't know about it yet because the light hasn't reached us.
Yeah.
Well, if I ask this correctly, then it will be a good segue onto what could possibly be our next bit. But
Okay.
I've been told that if you were to somehow figure out a way to effectively and efficiently capture and, well, not necessarily capture is probably the poor word, but to observe neutrinos from stars, then is it true that these stars, before they die, give off a large burst of neutrinos that we could possibly detect and therefore determine whether a supernova was about to happen?
Oh yeah, definitely. It's even more neat than that. So when the central explosion goes off, you get a lot of light from the supernova that is starting, but you also get a lot of neutrinos from that initial supernova explosion at the end when you run out of everything except iron. Except the light that is given off by the explosion still has to travel through all these layers of material that have been ejected over the last final stages. So actually, the light you see in the supernova is kind of delayed by the material expanding and letting the light get through. While the neutrinos don't interact with normal matter very much, so they would pass right through like X-rays and reach us way earlier. So then you could have a bit of a head warning, maybe a few hours or a few days.
Is there any chance that that sort of event has a special name? Maybe a Wolf-Rayet Star, unless I've made a wrong.
Nice segue.
Yeah.
That is a nice segue.
Yeah, that actually brings us really to our next question. So Nagi has been
You're
asking
welcome.
about Wolf-Rayet Stars, and his question was, they are described as leftover cores of main sequence stars. So are they actually stellar remnants? Because he thought there'd be only white dwarfs, neutron stars, or black holes after a star died.
Right. So let's go to basics. What's a Wolf-Rayet Star? So unhelpfully, a Wolf-Rayet Star is only called like that because it's a star with a large amount of carbon on the surface. Now, that's because that's what it was detected as. They're very rare. It's very rare to have a star with a lot of carbon on the surface because carbon tends to sink in the center. It's a lot more heavy than hydrogen. So when a star reaches the point where it's making a lot of carbon, it's in those final stages of fusing and getting all this heavy stuff, the carbon should stay hidden in the center. But it doesn't. When we only know about 100 of those guys in the Milky Way, so very rare event. There's a few ways that we think you can get that. So it's they're not all Wolf-Rayet stars have the same past history, but they're called that because they have the carbon on the surface instead of in the center. So there's two ways you can basically get that, and the most likely one is what you hinted at. It's the very, very last stages of a star just before a supernova, when basically the central process of heat production is starting to shut down and all the layers are starting to mix way more than they should. You get what is called a convection process. where basically the material gets dredged up to the surface by big currents from the core that's starting to shut down. And that can sort of dredge up the carbon to the surface, and you get a Wolf-Rayet star. And in Elite, like in real life, very often these Wolf-Rayet stars are at the center of small nebulae. So you've probably noticed if you fly around Elite a bit, every time you find a Wolf-Rayet star, there's a small nebula around it. And that's actually the leftover external shells that the star has already sort of ejected in its process of approaching a supernova.
So it's not a stellar remnant per se.
Not as such. It's actually just before a supernova. The central production might have already shut down, or it might be in the process of shutting down. It's not clear. And we don't expect them to live very long either, although we've never seen one explode because they're so rare. We expect that they would explode in a supernova, so we're kind of monitoring all of them.
Yeah,
So
it could
it's
happen anytime.
sort of like a stellar warning rather than a stellar remnant.
Yeah, pretty much.
Like,
Yeah.
or
But
to put it in
basically-
anime terms, death flag.
Yeah. It's death flag. Like something's about to go down here. But there could be more like crazy ways to get stars with lots of carbon on the surface. Like if you had a normal star that's ejecting all its outer layers because it's spinning really fast, or and then it's dying, so it's getting mixed. So it can happen to small stars too. It just takes a really strange history to get that. Small Wolf-Rayet stars are really, really rare. We only know like 10 or so. But because it's
That's
just
really-
defined by having carbon on the surface instead of the center. It's not like a specific history that gets you there.
So it's not specifically like they're depicted in Elite where they're all blue.
No, they're
Well,
not
actually, no, they're all
all
white.
types. Yeah, no, they're not all white.
Oh, no,
It
no,
can
no, they're
be-
not all white. I've literally got one on the stream right now that is literally a neon pink that I found.
Whoa.
It's a neon.
you
it's
see,
a
that's
it's a
the thing.
neon
Pink
pink
has
Wolf-Rayet.
different
But
colours.
here's the thing, and this is what we're here to talk about: how accurately portrayed are some of these stars in Elite? Because, like I said, I have a neon pink Wolf-Rayet on the stream.
I need to see this.
Well,
even if it's
we've
in
never seen one,
thing.
but there's no reason it couldn't happen if it had a very interesting history for that to happen. Like maybe it's spinning really fast. That would do it. So it started off big. It was big enough to get to make lots of carbon really quickly, and then it started spinning and losing its outer layers, like something like that. Some sort of very strange history. It's not like impossible to get there. Just we haven't seen any of them. I think the least bright Wolf-Rayet stars are M class.
So
Okay.
yeah, I've got it.
I
I've got a
just-
photo on stream. It's
Yeah, I'm
yeah.
watching the stream, but there's ads. Ugh.
I must be an idiot because I am looking through the channels and,
And
I
that's-
cannot find the link to it.
There's no link. It's just the stream. It's twitch.distantradio or YouTube/distantradio. We set those up pretty quickly. But yeah, that's a still image of me in front of a Wolf-Rayet, in front of a star that looks like, I would say maybe a T-class brown dwarf, like a really hot one. But it's a Wolf-Rayet. That's a Wolf-Rayet right there.
Yeah, I mean, why not? I'm sure if we saw one in real life, we could come up with ways to explain it, for sure. It's not impossible. Elite is cool.
So you're
Yeah,
saying that the strangeness and weirdness of Elite is actually possible. It's even if it's
Not
not
all of it,
even if
but
it's
a
not
lot of it.
always accurate, it is possible.
It's not all possible. Some things are like just wrong and impossible. But
Name
but
one thing.
most-
Name it, please. I'm curious.
Remember when those planets collided by just passing through each other?
Oh, yeah.
Okay.
That's a fair.
That's all right. That's
So cool.
that's a game mechanic
That's a-
thing. That's we're not talking about that. We're talking about the
What?
visual.
Wait, no,
we're talking about the
no.
representation.
What happens when you meet what happens when an immovable object? I'm messing this up. What that is
when an unstoppable force meets an immovable object? We already know that when what's his name met the Blob. When Juggernaut met the Blob, it was already resolved. What happens is that the immovable
17, I don't get that reference.
the immovable force actually repositions the space around the immovable object. So the immovable object technically does not move, but the entire universe
it
moves
relative to the-
around it because the unstoppable force is unstoppable. So technically, they all still are
So say an
accurate.
immovable object exists.
No.
is to say that something that we
See,
can
here's what you
interact with
It's
as
a
part of the universe
philosophical thing.
directly.
You brought a comic nerd into this shit, and now you're gonna get told. All right.
It's a philosophical question at that point.
Well, it's nitpicking.
It's not.
Yeah,
No,
there's not
they
a-
proved it. They said that the immovable object does not move. The unstoppable force also continues to move, but the space around the immovable object is shifted around the unstoppable
Right.
force. So that they continue to hold their they
requires a
can.
direction and a position a direction and a magnitude, and so for it to be moving something that isn't moving.
No. Look, I spent $15 on
Okay,
3
okay.
comics.
Please.
I know what I'm
Ridiculous,
talking
guys.
about.
Can I just say?
Yeah, you're a professional, Shank.
Can I just say immovable with respect to what?
Yes,
Because if I'm
exactly.
moving
That's the point.
Okay.
That is the point. The
Okay,
space
we made that,
around
okay,
the.
let's get back to
move on.
science.
Let's
Okay.
bring it back into the
Okay.
real plane.
Next
Okay, so-
question
okay,
by
fair-
Dr.
fair
Nag.
enough.
That's a poor math
Yes.
reference. I'm sorry.
He has been asking about star with ring systems. Are those a
yes.
thing? And if yes, how rare or common are they?
Oh, I love this question. This is great. This is my okay. So stars with rings around them, can they exist? Yes, they do. We even have pictures of some. I'm very glad. I'm going to put some on the stream.
What about us? We have the asteroid belt. What makes that different from a ring system?
Well, I guess in Elite they look a bit more extended, right? They go all the way to the center around the star,
right.
and they extend quite far out. But it's true that they're basically the same. Now the thing is.
Oh wait, actually, no. That's an unfair distinction because the asteroid belt it's only kept stable by Mars and Jupiter, isn't it?
Yeah, pretty much.
So it's an unfair distinction. I apologize.
Sorry, I'm just looking for this picture to send. Oh god, I hate Windows. Where is everything? What's going
Hang on, we can
on?
just talk about the Kuiper belt then.
Ever heard of a decent folder structure? Sorry. No, we're
So
not here
anyway,
to rip on Windows.
So, I'm here to rip on Windows any day.
Okay.
Unfortunately, I
alright.
can't
So
rip on Windows.
basically-
Did you find the picture?
Refused.
Well, I do have it, but I'm trying to upload it, and I'm failing miserably. It's really sad.
Send it to me. Send it to my email.
Drag and drop it into the radio chatter, or yeah, send it to someone else.
Doo-doo-doo.
Error.
All right, there's one.
Error.
This is my own.
Sorry, I can do that
technical
very well. and
incompetence.
It's quite obnoxious.
Wait, where's?
Whoops,
Where did
there's
you
one
post it?
in the chat,
Aha.
and there's a second one. So there's a star there at the center, and a big disc of stuff around it. And it's,
Ooh, wow,
so
that's.
we now have
oh,
about.
wow. Wait, hold on.
I know.
Is that an actual legitimate and accurate photo?
Yep, that is an actual photo.
Do you
God,
by
that's
any chance have a
beautiful.
name
That's
of that system?
Fucking gorgeous.
Because that is, yes, I agree with Chank here.
It's called TW Hydri in the Hydra constellation.
It's a
Yeah,
bit
the little thing
blurry.
I know. Well, it's actually gotten by exactly the same technique as the black hole image. It's just a lot bigger, but it's the same technique. You only need one telescope to get an image like this. You don't have to combine all of the telescopes in the world.
That's
the idea is
fucking
the same.
beautiful. Holy shit.
I know. I really like that one. So the thing is, they're not just rings around the planet that live forever, right? When you have rings like this around the star, what it actually is a protoplanetary disk. So it's a disk where planets are currently being born. So you can see in that image, there's these gaps, these like black gaps in the disks. And that's actually where new planets are currently forming. They're all tiny, and then they start gathering all the bits when they go around and growing. So it's actually a young solar system.
So,
actually.
So what you're saying is if we looked at this in maybe another, well, on human scales, it's hard to say. If we looked at this in maybe 10,000 years, we would actually see pinpoints of light in those gaps that might be planets forming.
Yeah, I mean, in some cases, we are actually there. We know about like a dozen or so of these stars with rings. I'm trying to upload the other ones, but my internet is not working for some reason. And for some of them, you can actually kind of see where the tiny blobs are, like on their way to going round and clearing it up.
Oh, Kenny is asking, are those just accretion discs? Do stars have accretion discs?
Accretion disk is a black hole, isn't it?
Yeah.
Yes.
An accretion disk is matter falling in around something. So you have a something like a star or a black hole, and then stuff falls in and forms a disk. And some of that disk is continuously falling in the center.
If you have enough things falling in towards a star, but you have enough other things like spinning past it or flying by and knocking it out of orbit and all this shit, you would probably assume you would get those kind of dark rings where it's like something either hit something else and caused a balanced orbit in a way to create possibly a planet orbiting a star.
Yeah, pretty much. So the initial trigger, the first thing that makes it start, can be a range of things. It can be just a chance collision of some asteroids, or it can be something passing nearby and perturbing it in some way. But once you have a small asteroid that starts, it will just grow and grow, and every time it goes around, like vacuum a bit more of the material, and get these gaps bigger and bigger every time. It's quite neat, I think. In Elite, they're not quite as beautiful. I've seen a few stars with rings, but they usually don't have planets in the gaps or things like that. It's not that detailed.
No. Well, what it can still be put in right. They might update it at some point. Perhaps.
I do think this image is going to be my new wallpaper, because my old wallpaper has been for about a month the image that I posted. No. It was before the black hole. The wallpaper I used to have was of Rich Evans and what's his name from Red Letter Meter, and he's like, how does it feel to watch all your favorite franchises that you grew up with go down in flames? It's like, it feels great. And that's been my wallpaper for months. And now that
too depressing.
Well, I hate myself, so it makes sense. But that is so beautiful. That is such a beautiful photo. That's my new wall. I'm gonna rotate it, of course, but that's my new wallpaper.
And the thing on the side, by the way, the little square, that's like the zoomed version. That's at about the same distance away from the star that the Earth is. So for a scale.
That's a huge disk.
Yeah.
Not
Big
bad.
disc.
I need another photo of it. One without the zoom in. But let's get back to science. Well, we've been there all the time, but
But I didn't see the thing that sucks.
what? Sucking
What?
things. Look at a black hole. Those all suck.
I'll post it. I'll look in
No,
radio.
I was
Look in
gonna
radio
do a
chatter.
joke, but it didn't. No.
What? Radio chatter?
There you go. There you go. In radio chatter, that's been my wallpaper for a month.
Wow,
It's
come on,
no
Shane.
longer my
Okay.
wallpaper.
So, that's good. Next question. Oh my god, it's all been asked by Nagi. Well, let's just finish off the disc thing. So we
Actually, can I ask a question then?
Right?
Can I ask a question that's outside of this?
Okay.
Because we've talked a lot about
Yeah, go on.
we've talked a lot about. Are you still here, Showball?
Yeah.
Because you're the one I'm asking this to. We've talked about main sequence, and we've kind of edged on S-class and carbon stars, and these K2s and these massive stars. How accurate is their, shall we say, proliferation through Elite Dangerous? Is that realistic to what we expect to see? And then beyond that, the post death stars, white dwarfs, neutrons, black holes, are they at a level that we actually expect to see them at in Elite Dangerous?
I have a counter question.
Yeah.
Let's start. Let's get a response first, and then you can counter. Okay.
Nah. Come on, Chank. You've been talking all the time, so let Selfish Pie ask his question too.
Oh no, it's not actually like a counter question. It's more jokingly, but I do
God,
mean it.
we've
Can someone please define what was it?
Proliferous means?
That word.
Proliferance.
Proliferation.
Is the act of-
Proliferation.
Yes.
The express distribution of a thing.
Ah.
abundance.
Hey, there you go. That's
A rapid
yeah.
increase in the number of or amount of something.
Sometimes I am a dumb redneck, but sometimes I forget that I'm a classically trained in linguistics, and that happens. I apologize.
Well, no, don't worry. I'm 17. I have a natural lack of vocabulary.
Oh, you're making
That
up
joke.
for it very well.
My jokes are not landing. Why? Do you dislike me?
No. What you needed to say was, "I apologize. I'm 12, and what is this?"
Oh my
See,
god.
there
I'm
you
14
go.
and
That's how you
17.
make a joke. Come on. Okay,
come on.
still
Cut him some
learning.
slack.
you know what?
He's 12. What is this? He can't make such good jokes.
Selfish pie.
Well.
Selfish pie. Don't worry. Selfish pie. You know what? I've got a whole other week of holiday. You and I were gonna sit and chat, and I'm gonna teach you how to tell jokes, and you're gonna be the king of comedy.
Okay. That's good. Anyway,
That's all well and
Anyway.
good, but the question I had.
okay. Is your question answered, Shank?
Yes.
Oh, yeah.
No,
sure.
my
Okay.
question is not answered.
So
my
the-
question is, how accurate
The
is?
abundances of stars.
Yes, thank you.
So all the main sequence stars are very accurate because we know exactly what the true answer is. So thanks to this mapping mission called Gaia that went up a few years ago, we're actually mapping all of the stars around the sun and getting our first galaxy map, or at least a map of our surroundings. And these stars, O to M, they're very abundant. They're hard to miss, so they're probably quite accurate. The more exotic stuff, like neutron stars, white dwarfs, black holes, or brown dwarfs, that's probably less accurate, but mostly because it's not very well known. So I think when Elite was first created, they had to pick basically how frequent some types of stars were to put into the stellar forge. Except some of the values are really poorly known, and they might turn out to be something different. So they
Oh,
went a bit
the Soul
overboard.
Cross,
I
of
think.
course.
I mean, they did their best.
The literal blackout on the X and Z axis from Sol, that there are no black holes and no neutrons, except for what we know exist, like Sagittarius A, and the Jackson's Lighthouse, like from
Yeah,
Sol,
pretty
and
much.
like, of course, this is my wheelhouse. It's like everybody's like, yeah, Chank knows neutrons. Yeah, from Sol, if you go minus 500 plus 500 on X or Z, there are no neutrons. But in reality, that's very unrealistic.
Yeah, and then in some parts of the galaxy, there's a lot of neutrons all in one place, and above and below the disk, there's slightly more on average. That's probably accurate,
yeah,
but
the plus
we don't know that many.
plus 1000 Y minus 1000 Y. They're literally platters of neutron stars, and it doesn't like
So many.
it's fun to know that exists, but it doesn't seem realistic. It doesn't seem accurate to how space should work.
It could be. So we've never seen in real life like a group of neutron stars, but we have seen globular clusters, which are basically big groups of stars all born at the same time, more or less, and really tightly packed together. So presumably one day they will all die roughly at the same time, and you would have sort of a degenerate remnant graveyard that's very dense. It's possible, though we haven't seen one yet. So neutrons may be accurate, but it's hard to know for sure. Brown dwarfs, I think they went a bit overboard in Elite compared to real life, because we really don't know how many brown dwarfs there are. They're very easy to miss. They don't emit a lot of light. How many are there compared to main sequence stars is very, very uncertain. It could be off. It could be 2 times more or 5 times less.
So
You just have to pick a number.
So while we're at the topic of commonness in stars or star types, Nagi has been asking if binary stars are more common in real life than in Elite, and why are they so common?
It's probably quite similar. So a lot of stars that are in binaries, actually, maybe about half, roughly. It's sometimes hard to spot. And sometimes, of course, they can be in more than binaries. You can have systems of 3 or 4 or 5 going up. I think some of the systems in Elite are very crazy, but some of the ones we see in real life are very crazy too. I think the biggest ones we've seen have 7 stars all in one system, or going around each other in weird configurations.
Isn't I don't know the name of this. You probably will, Shoba, but the record. I was told somewhere it was 8.
I haven't seen that one. Could be. The one that's close to Earth, the one that people can see by eye, the most crazy system, is Alcor and Mizar in Polaris. So in the Big Dipper, there's a double star in the handle. And it looks like a double star. If you look at it with your naked eyes, if you have really good eyes, or with binoculars, you can clearly see 2. But actually, there's 6. It's a crazy system. It's 2 times 2 plus 2. You have 2 doubles going around each other, and then an additional double further out. It does happen.
What would happen if one of the pairs, one of the stars of a pair, would die before the other?
Yeah, that's a good question too. So usually the system would separate. So when how do you say, when giant stars die, when they go in the final stage and they become a supernova briefly, and then they leave behind a very dense core called a degenerate star, usually a white dwarf or a neutron star. And when that final process happens, actually they get a kick. So they get a kick in a random direction in the very last stage of this process. And that's because the way they're losing mass, the way they're exploding, it's roughly spherical, but it's not perfectly symmetric. It will always prefer slightly one side over the other. And because the explosion is not symmetric, at the final stage, they get kicked. And that kick is actually quite big. And it's enough to break them out of most doubles, unless they're quite close. So if you have a star that's in a binary with a star very far away, then when that star becomes a white dwarf, it will escape. And that's been seen quite commonly in the galaxy. So that's one thing in Elite that probably shouldn't exist. If you have a white dwarf in a binary of a star very, very far away, that would have probably been destroyed when the first star died, actually.
Good to know. I hope Nagi hears all the answers to those questions. Yeah, he's been the one asking them, so he should at least get him. Hear him. Anyway.
While we're on topic,
yeah,
sorry. While we're on topic, we can go through the top 3 best crazy systems. Yeah, let me find them.
Oh yeah, we can do that.
Yes,
so
I need to take these.
All right, so do I have pictures? I don't have. I can get a picture. I can get a picture of this. So there's only 3 known systems of degenerate stars orbiting each other. So systems that are completely made of dead things. There's one that's a white dwarf binary that are very close to each other. They go around in about 4 hours. Then you have a third white dwarf slightly more far away. So it's a triple white dwarf system. There is one. And we only found that about 5 years ago. So, that one doesn't have a picture that I can find. Okay. Triple white dwarf is this one. Okay, I can take a picture of this. There is another triple white dwarf, the only other one that was found last year.
Okay.
That actually does look cool. So I'm just getting a picture. Give me a sec.
Yeah.
Up.
Curious.
Isn't it possible that if one star dies before the other, that the smaller star will feed off of the larger one and it will do like a repeating supernova thing? Sort of thing. Well, didn't that happen a while ago?
No, we've seen systems like that. Yeah, if stars end up too close, or if one star enters the giant phase and puffs up, like you described earlier, it gets into this final stage and it expands. Then that envelope can actually reach a companion if that companion is really close, and at that point they will get connected, sort of. Either they feed off of each other, or in some cases, one star can even end up inside the other one, like a cannibal situation. There's even been a case of that, which is completely crazy.
So
wait, how would you even know that sort of thing?
Because you see the star wobble. So when you have 2 stars, they actually go around the common center of mass. So in this case, it's going around like a bit of itself, which is inside, which is so weird. You just get a wobbly star.
Jank, you seem confused.
No. I was just wondering. So, how do I say this?
Yeah.
In Elite, in Elite, when we see things like Planet of Death, or as I'm showing on stream, the Planet of Slightly Lesser Death. That's literally what I've called it, and the guys who do the POI project have said Planet of Slightly Lesser Death is okay because Mon de Mort is already taken. It's a planet that orbits almost perpendicular to the jet cones of a white dwarf, which in itself is already interesting, but it orbits a binary where the white dwarf is right next to an M class. That wouldn't happen. Well, I don't want to say naturally. Those would not form in and of themselves, shall we say. That secondary star has to be something captured. It cannot be something that was formed there at the same time as the white dwarf.
If it's really close,
Oh, it's
there's ways.
really close. It's
There are ways. So, for example, if there is stripping going on, if it's actually continuously losing mass throughout its life, it can, in some cases, start to spiral in and just get closer over time, depending on how exactly it's losing mass. So it can actually get increasingly close just over a long, long, long time. Plus, it's stable. As long as they don't get too close, there's nothing that's going to sort of ruin the internal structure of the star or anything. You can have a binary that's quite close without really bothering each other. Not to the extent of Elite. In Elite, some of the binaries are way too close. I've seen binaries in Elite that for sure would be getting material off of each other.
I've seen
For sure.
binaries where they're inside of each other. It legitimately looks like a. In fact, I think if you go deep diving through some of the old, like really old messages from like a few months or maybe a month ago, there's like actual pictures of like these two. I think, Chank, haven't you got a picture of like two stars where it's like it legitimately looks just like a snowman?
Oh yeah. Oh geez, yeah. Actually, Michael went back there too. It's a trinary.
I think yeah, it was
Where,
one of you guys.
Oh yeah, that luminosity picture, right?
Yeah, it's the luminosity picture that I took. It's a trinary where basically there are 3 stars. They're all same. I think it's like a KMM series, but the 2 ones that are really at the core are literally so close that you can't in Elite you can't fly between them without like their gravitational spheres of influence in the game. By the way, anybody who hasn't realized this yet, when you're flying towards a planet and you see those little blue rings around something, that's the gravitational sphere of influence. But the spheres of influence of these 2 stars literally overlap. So even flying between the 2 main stars, you are technically scooping off of both of their coronas. Like
I've seen things like that.
They're way too close to actually be real. That is not possible.
That's too much, because by that point they would start sharing material massively. You'd see them being connected, basically.
Like it looks cool. It's visually stunning, but what would actually be more stunning would be to say these 2 stars are basically an individual unit, and they are shedding material off of each other as they slowly collapse into one another.
Yeah, that would be
a star in the
even
shape
more
of a peanut.
Cool. Yeah.
Yeah, I can't find the picture now, so Chank, you have to look it up yourself. Yeah, where were we? Yeah, we were at having a much larger star eating its smaller companion. So we will move on from there. I think we covered binary neutron stars, binary white dwarfs, or binary neutron and white dwarfs. Have we talked about that? Kenny
Let's
has been
see.
asking
I
about
don't
those.
think we've talked about binary neutron stars.
So yeah, so
Oh,
neutron
I want to hear
stars
about
and white
neutrons.
dwarfs, they have
I want to hear about neutrons. Hold on. Let me take my pants
Let her
off.
talk.
they are cool. Both white dwarfs and neutron stars, they are really cool.
Oh, I don't care about white
in
dwarfs.
terms
I want to hear about neutrons. So let me take my pants off, and then we're good to go.
Okay, neutron, binary neutrons.
By the way, that's a
Binary
joke,
neutrons.
but
Dang.
anybody who doesn't know
No,
me,
it's okay.
yeah,
Yeah,
in the
Chank
game,
parties with his pants down.
in Elite, yes, I have more neutrons discovered then you have systems discovered. I'm Chang Satome. Deal with it. It's a fact.
Challenge accepted.
Okay.
I
Anyway,
believe that.
now
No, I found a completely pristine field of neutrons 3 weeks ago. There was none of them were claimed. I was so happy. I just went round in a
Cool.
loop.
so any of them binaries?
So why is that? Why
Yes.
were you so fascinated with neutrons?
Well, because they're a whole new type of matter that we can't even recreate in our labs, right? It's what happens when you really force matter to be compressed way more than it wants to be.
Oh my god, I didn't realize I was dialing a 900 number here. Ooh.
I don't know what that means. What's going on?
What?
That was an analogy. Well, a metaphor. Yeah. So binary neutrons. Come, tell us.
Wait,
Possible?
whoa,
Yes,
whoa,
no?
whoa, hang on. I want to get this joke. Because I don't like being not included.
All right.
Yeah,
So
you got more
let
than
me
you asked for.
explain. Let me explain a joke to him. In the U.S.,
So it's not funny anymore.
0800 numbers are free to call. 0900
Right.
numbers are phone calls where you pay. It's basically you pay to call the number. Most sex chat numbers are 0900 numbers, or at least they were, and therefore the joke was I didn't realize this was a 0900 chat.
He didn't realize he had to pay. Anyway,
That's
yeah.
funny.
Now, again, binary neutron stars.
Binary remnants. Let's include everyone. Let's include all
Yes.
the remnants because
Binary black holes. Yeah, we know.
Because
those
we're
exist.
inclusive here.
Okay, let's go from more common to less common, right? So I mentioned
Kenny is
before that
actually
when the
correcting me.
Jack.
Kenny says it's 1900, not 0900.
fair enough. Not sure what it is in the UK, but or 100.
I mean, I wouldn't know.
Anyway,
Right, binary remnants in binaries. They do happen. So as I mentioned before, basically when the star dies, it gets a random kick, which makes it very hard for it to stay in a binary with another main sequence star. In total, we only know about 3,000 cases of a white dwarf and a normal star in a binary. It happens. It can still keep a companion if they're close by, so that's okay. White dwarf plus white dwarf, quite common too. There's about 400 of them that are known. Again, you have to start with stars quite close together, otherwise when the first one dies, the other one will just be stuck behind and end up alone. And more than two, there's only the one I posted, which is a picture of 3 white dwarfs in one system, and there's 2 more that have less good pictures.
so would it be possible for if let's say there are 2 distinct binary systems, or let's say 2 distinct binary systems relatively close to each other, but not in a system with each other. If each one of those in each of those systems, one of the stars goes neutron and gets that kick to be kicked out, would it be possible that those 2 stars would catch each other if they were kicked in the same in each other's direction?
It's possible, but exceedingly unlikely.
I like exceedingly unlikely.
Exceedingly unlikely. Once it flies off, it's exceedingly unlikely it will ever encounter another star to hook up with. So binaries have been together since day one. They don't form late in life. Stars all marry young.
So if I find
Soulmates.
something like this, I'm gonna get a Nobel Prize, right?
Well, how would you prove that they came together late? That's the other
No,
question.
I'm gonna prove it a million years in the future. Anyway,
and as
okay.
for neutron stars are even more extreme than white dwarfs. They're
Oh
only
yeah,
formed
tell me about
with a
neutron
lot-
stars.
Yeah.
Chang.
Okay.
Stop
Calm
drooling,
down.
Chang.
Well, let's go from the start then. So you have your massive star. It stops being able to fuse iron into heavier stuff. It dies. All the outer layers explode. You have a nebula. All the outer stuff is gone. Okay, you're only left with the core. Now, if the core is made of the core by this point is made mostly of iron with some leftover stuff from before, so some carbon, some magnesium, all sorts of stuff, all compressed in the center. So all that stuff has no like reactions in the center to stop it from collapsing. So you compress it and you compress it more and more until you only get the nucleus of the atoms with all the electrons just flying around. So you get a big soup of many different cores of atoms, many different nuclei of atoms pressed together in a big messy soup. That's a white dwarf, is the most common remnant. So when you only have the cores of the leftover nuclear waste, basically.
White dwarfs are vicious.
And
We
it
don't
takes a
want
long
them.
time to cool down. Yeah. It's all nuclear waste in the end. All carbon is nuclear waste.
We are all made of
actually,
nuclear waste.
can I ask you then, as the guy who has a dangerously sexual obsession with neutrons. What
Hey, we all have our thing, man.
what is the distinguishing feature between what creates and defines a white dwarf to neutron to black hole?
Perfect
Is
segue.
it just mass?
Yeah.
Is it just mass?
All right. So the base answer is yes, it is just mass. But let's think what happens to this bowl of nuclear waste that you have. So at first, it will still be quite hot because it spent literally billions of years being heated up. It's super hot. It's like a plasma, like basically still fire in terms of its composition. So at first, that heat will be enough from stopping it collapsing. All the electrons flying around are still moving with some speed. They're bouncing against stuff, and all the bouncing is giving it some pressure. It's not completely condensed and collapsed yet. Now, eventually, it will cool down. All the electrons will stop whizzing around and providing pressure, keeping it up, and all the electrons settle to as low energy as they can. But and that's when you really get a white dwarf per se. It's stable. So a lot of white dwarfs in Elite have weird names, right? So you have the A, the B, and the O types and the Cs. And that's basically because they're not done settling. They're not in this final stage yet. They're still cooling down and being supported only by the remnant electron energy.
Yeah, oh
And
yeah,
they
because
still have a bit of shaking going on.
yeah, in Elite we have the DOA, DOB, DVB, DVC, DV, all that nonsense and stuff.
Yeah.
Like
And that's basically because they're still shaking.
when you have in Elite, a black hole is a black hole, a neutron star is a neutron star. But when you have white dwarfs, there's like 10 different types of white dwarfs.
Yep. And that's the reason, is because it's made up of a lot of mix of leftover materials. So depending how much iron you have, how much carbon, and how close it is to completely cooled down, it can be shaking, it can be spinning, it can be doing all sorts of crazy stuff.
So
white dwarfs are actually really complicated.
So much like in Elite, we have we have our main sequence stars, and you got your classification, you got your luminosity, then you have your heat, and you have your size. So you can have you can have an M class star, but it can range among almost 20 different types of what M class star it is. With white dwarfs, you have multiple classifications versus a neutron is just a neutron. A black hole is just a black hole. I mean, well, a black hole is just a black hole, except for the supermassive black holes that we have. Those kind of defy definition in a way.
Pretty much. No, but that's basically the reason, because white dwarfs are still quite complicated. Neutron stars, in comparison, they're not. So a neutron star is on a whole different level compared to a white dwarf. In a white dwarf, you still have, even when it's done cooling down, let's say it's completely settled, all the electrons inside of it are still minimally bouncing around. Because of quantum mechanics, the amount of just baseline bouncing around of electrons against each other is enough to stop it collapsing any further. And that's kind of okay. It's still like an understandable form of matter. You go to neutron stars and the electrons just give up, right? At that point, a neutron star is when you have even more mass, that this process cannot even keep the remnant from collapsing even more. So the baseline electron pressure is not even enough. It collapses to a whole different state of matter that we definitely cannot make on Earth at all.
I mean, in the game, you're in Elite. You're saying they actually did a good job of accurately representing that there is these different statuses to all these various stars we have out here.
Yeah, so basically the main sequence stars are classified by their heat, the giant ones are classified by their size, the white dwarfs are classified by their settling level, basically. But the neutron stars are just a ball of neutrons. It's when all other means of supporting your star have given up. So heat is not enough, there's no fusion. Electrons bouncing around are not enough, it's just too heavy. And the last resort to still keep you from becoming a black hole is neutron pressure. And that's to the point where even the protons, in an attempt to keep the star up from collapsing, they actually turn into neutrons, because that's the only way to keep it up. It becomes purely neutrons, and all the electrons just fly away. So it's...
Well, hang on. I was told that the electrons join with the protons to become neutrons, giving off light in that.
Kinda. So the protons emit an anti-electron, and the anti-electrons destroy the electrons. So the protons turn into neutrons because they have to. It's the only way to provide pressure.
Ah, right, okay.
So
the protons turn into neutrons by giving off their charge to become right.
Yeah, they give off their charge, and their charge just interacts with the electrons, makes a much bigger explosion. When a neutron star is born, you have a much bigger explosion because of this giving up of protons.
Mm-hmm.
And you end up with a very, very pure matter in the center. It's just made of neutrons. And the only properties left are the size, which is the same as the mass, because it's just made of one stuff, and how fast it's spinning. It still has a spin, and it can still have also a magnetic field. But that's it. There's no different types. It's all made of the same stuff. It's all unified in a desperate attempt to not collapse.
How can a neutral thing really cool. Have a magnetic field?
It's complicated.
Well, that's what we're here for.
It's due
Come
to
on, throw it. What?
It's partially due to quarks, and it's due to magnetization cannot be easily lost, right? So say that your star to start with had a very weak magnetic field before it died. Well, now that magnetic field can't really be lost. So it all ends up compressed in the center. And on the large scale, it's still quite weak, but because the thing it's collapsed in on is so small, on the surface of that, there can be a lot of magnetic fields. And they kind of run along the surface and sort of guide the atmosphere of the neutron star. Because yes, a neutron star also has a kind of atmosphere made up of all the electrons that were sent off and the last protons that are still turning into neutrons and joining in. So there is a thin atmosphere of very ionized particles, really powerful ions and magnetic fields on the surface. And that's what gives them jets. So yeah, they give them the jets we see too.
Okay, that brings us to Nagi's question. The next question Nagi had, and that was about Neutron Star and white dwarf jets. So the first question was if they exist, but that's a yes. So, and if yes, what are they made of? So that's pretty much also answered.
Yeah, in the case of neutron stars, it's actually emitted from the surface atmosphere, because the magnetic fields are so concentrated, they can accelerate these particles into jets, a lot like the Large Hadron Collider, like the LHC. It's the same process. You have strong magnetic fields, so anything falling in the gap will be accelerated out super fast.
Okay. Yet now let's do a question that is completely unrelated, but we've skipped it and I wanted to ask it for a while now. Is the abyss an actual possibility in a galaxy? Kenny has been asking that.
Wait,
What's the abyss?
What's?
Okay, help me out here, Chank. What's the abyss?
Oh my goodness! You want me to? Okay, so the abyss is, and I think it's just because of how we are incapable, honestly, of mapping the opposite side of the galaxy. Is how I think Elite has tried to do their best in trying to portray the galaxy and its density, as I call it, in real terms as of how we recognize how the galaxy in reality actually exists. But because we cannot see to the direct opposite end of our own galaxy, in Elite we have this thing that we call the abyss, and that is what that's what we're dealing with Beagle Point and everybody heading on their way out to the last waypoint. The abyss is it's purely constructed by an algorithm that is Stellar Forge. It says Stellar Forge says, here's what we expect to exist out here, but we cannot say that we know anything for real. So star density is very limited and lacking on the opposite, literally directly opposite of Sagittarius A, the core, from us. So some people have asked and questioned, is that realistic? And I argue that, I don't argue because I don't really care, but I don't think it is. I think that the density out on the opposite side would be much more than what we see in the game. I think in reality it's probably a lot higher than what we see, but because we can't see it in Stellar Forge, it's programmed to represent the fact that we can't see that. And so there is a lot of empty space out here at the far northern edge of the galactic rim.
Okay,
Fair
now
enough.
that's clarified.
Okay. Well, it's true that most spiral galaxies that we see outside the Milky Way are quite symmetric. So you wouldn't expect one side to have a lot less stars than the other side. Spiral galaxies that have arms, like the Milky Way, they do tend to be more or less symmetric. Although they could have, say, if they have only 3 arms, then they're not symmetric down the middle. They're symmetric like in a triangle pattern. It depends how many arms your galaxy has. Because actually, we're not even sure how many arms our Milky Way has. That's how
can't
poorly
see, really.
known it is.
Oh
it's
yeah.
not
Well, I
clear.
mean, yeah. Even
small
Elite,
tangent.
the estimation is what is it's 4 spiral arms in Elite. I think it is what they built it on. Am I
They
wrong?
had to pick, right? They had to. If you were going to make a scale model of the galaxy, you have to assume a lot of things. And you're totally right that we have no idea in real life what it is. I mean, our best mapping... Yeah.
Small tangent. What is the Or well, how do I word this? What is the
1, 2, 3, 4. Yeah.
most commonly sort of accepted estimation for how many arms we have? Just out of curiosity.
4 probably. But
okay.
3,
Yeah,
but 3 and
so-
5 have also been argued.
Yeah, so I just did a quick map check of the Gal map. It's built off of a built off a 4-arm spiral. They look really close together. It's hard to point them out, but when you get out towards the edges, you can say there's 1, 2, 3, 4. You can clearly see them in the Gal map in the game. The frontier Milky Way is definitely built off of a 4-arm spiral. You can see.
But let's not overestimate how much we know in real life, because our best current mapping effort, which is the Gaia satellite, even when that's complete, and that's using all the technology we have today and scanning the entire sky over and over, our best mapping effort is going to get 0.5% of our galaxy, right? Our real life galaxy map is 0.5% complete. We know a lot more stars in Elite than in real life. But basically, we have no idea.
Which is kind of awesome and also kind of disappointing. But from where we are in the galaxy, it's pretty much we're looking at a wall of stars that's hindering seeing us seeing everything else behind that.
Yeah.
Trying
So
to map the
yeah.
galaxy is like trying to draw your face without a mirror.
Yeah, I like that. Yeah, that's good.
So to check out the question, the abyss is something possible if the symmetry is right, but or even not right in that case, but we can say, right?
It's probably allowed.
It's
I don't
allowed,
think
yeah.
It's not impossible.
Well,
That's
I mean,
good,
Because we don't know much, right?
didn't we just realize? When was it? I literally came into this thing being
Well,
like,
when was
I
what?
literally came into this being like, I'm not going to talk at all. But it's like, now I'm here.
Yeah.
I love Michael. Yeah. But didn't we realize that? What was it? 2 or 3 months ago, that the Milky Way is not a flat spiral. It's got a kind of curve to it.
Oh yeah, that's right. It's slightly twisted. Ever so slightly.
Twisted how?
Wait, yeah,
Like if
hang
you get
on.
the
Wait,
Like,
you
imagine
wait, hold on, wait a second, hold on. I want to back the truck up. The dumb redneck knows this, but these guys don't.
It was in a lot of newspapers, to be fair. Right?
Yeah, I don't read newspapers anymore.
Ooh.
Well,
I'm internet.
Oh, this was
Okay.
big news,
Well, I
man.
read the BBC,
the Milky
so
Way is not flat.
that's
It's
clearly
not
why.
it's not a flat disc. The Milky Way.
Are there any pictures to what's it called, to give an impression? Because the only thing I can think of is taking a CD and bending it, or twist it. So
Well, no,
I
that's
can't really
exactly
imagine
it.
what the
Basically,
galaxy actually
if
looked
you
like.
had if you took a CD
Yeah, okay.
and you let it like melt slightly on your passenger seat on summer or something, it's kind of got a curve to it of something like 30 degrees or
right.
something, right?
I'm sending a picture
Cool.
using my high skills of picture sending. Oops, there we go. This is another example, not ours.
Right.
Ah,
Yeah, this. I saw this
It's-
picture.
It's
Okay.
wobbly.
how does it work? How do the stars actually stay in that strange region? That's
How do they stay in that alignment as they
Bent
orbit
off.
around the core at
Yes.
300,000
I mean, I just-
The answer
kilometers a
is
second?
they don't. Haha. They don't actually. Being twisted like this is most likely a temporary effect. It happens, for
Coincidental.
example, if a small satellite galaxy joined us recently. Like the Large Magellanic Clouds are currently falling into the Milky Way.
So
They're currently
it's-
being absorbed into the Milky Way. And because they came in at an angle, it's all a bit shaken up.
So
but
they haven't
usually,
settled yet.
yeah, it will resettle.
All right.
But
I
some
was-
galaxies are a bit twisted like this.
Now I have a moving picture in my head that actually makes sense.
Yeah, I was just thinking because this sort of thing it actually happens out at. It actually, well, not to the. I don't think it happens to like the extent that that image is uh substantiating, but this sort of thing happens out near Saturn, doesn't it, with the rings? Because the moons, I know. Oh, what one was it? Enceladus is a bad example because it's the source of one of the rings, but there's one of the moons where it's like in such an orbit that it goes and it causes like, or well, I don't know. Hang on, I'm gonna try again. It goes through the rings and it causes these waves, but the rings correct themselves again around it. Is this just a coincidental sort of similarity, or?
It's the same principle. It's because disks are very, very stable to this kind of perturbations. So even when they happen, they tend to fix themselves, whether it's around the planet or a star or at the size of a galaxy. Yeah, so that's very related. Actually, it's due to the universal stability of spirals.
It's
the one
just
I
still
I sent
baffling.
I sent the name of the one that I posted. That's actually a real one. It's just not ours.
Yeah, but it illustrates how it looked like.
Yeah.
And that it does a very good job at that because, yeah, it does.
And that's a good question actually. I would have for the elite devs, right? What would they do if it turns out our galaxy is warped and their map was wrong? Like I get they had to assume stuff when they made the elite galaxy, right? But what will they do if it turns out to be wrong? Will they retcon it, or will they just leave it?
Well,
That's the
maybe
the-
they leave it and take the new information for a second installment of the game.
DLC.
Another relaunch.
DLC warp.
That would be, well, maybe not the DLC, but like that would be fantastic. Oh, that would be the basis of them redoing Elite again, because Elite Dangerous itself was a relaunch. Or well, they weren't planning to make any sequels past Elite 2. So this was a complete relaunch, I believe, just with a different
it
name.
was crowdfunded after all.
Like in like Elite in the modern day was the sort of design principle behind it, wasn't it?
Yep.
Yeah.
Also, but regarding the next installment of a Elite Dangerous game, that was more like fear of it, because I'm actually hoping the game will keep going for another 5
Oh
years.
no,
or so,
definitely.
at least. So anyway,
Yeah, sorry.
we've been blasting. Yeah, no, not you, me. I've been digressing, but we've been blasting through all the questions, and I'm having trouble finding one that hasn't been answered yet. Are there any questions in the audience, in the chats, or anything we haven't answered yet, but in enough detail or something like that? Oh, there's a message.
Ooh.
I
No.
I actually do have a question we haven't gotten to.
Sri Lanka has been asking a question. Where was it?
I'm just getting put under the rug now, aren't I?
I'm sorry. Yeah,
Oh
Sri Lanka,
wait,
can you ask the
Basti has
question again?
one. Basti Wonder has one.
Go
Yes,
ahead.
where was it? It was just well, I am just going to read this out because unfortunately I can't think of a way to word this.
Yes.
Could you talk about Cepheids and other variable stars, principally the processes that make the pulsations?
Ooh.
What
Awesome.
does this mean, Shoba?
Cepheids are my second favorite type of stars.
Oh, I
Because they're
mispronounced it.
they're actually useful for cosmology. Now we get into it. Cepheids. So Cepheids are basically the most reliable type of variable stars. They're very common and they're very reliable. That means they always vary their luminosity at the same speed. And that's because basically they've reached the helium phase. You have a big star, it's done with most of its hydrogen, it's onto the helium part, and it's basically going to take turns using the helium and not using the helium. So it eats up the helium a bit too fast. It produces a lot of heat, it expands a bit. Now it's a bit not dense enough, so it has to stop eating the helium. Then it cools down, it restarts collapsing, and then now it's hot enough again to start eating the helium. So it goes in these phases, slightly too big and then small again, big and small again, in a very predictable, reliable fashion. That makes them super useful. Because basically, if a Cepheid is of a given brightness, it's always going to oscillate at the same speed. You know how fast it's oscillating, you know how bright it is. And that is the easiest way to measure distances to other galaxies. Because say you look at Andromeda and you see a Cepheid star in it, you can recognize it because it's pulsating very, very regularly. And you're like, oh, well, all the local Cepheids that have that speed are all exactly this brightness, all of them in the Milky Way. So that's handy. I guess that star over there in Andromeda is also the same brightness as these. And then you know how bright it's supposed to be. It looks quite dim, so you can work out how far it is. And that's how we measure distances to galaxies, or at least it was the first and most ancient way of doing it. Cepheids are what we call standard candles. If you know how fast they oscillate, you know their brightness. It's always the
Isn't it
same.
like
There was the connection I was missing.
Yeah.
Savage Pie, you were about to say something. Huh? Did he just die?
He went away. He disappeared.
Yeah, there you are again. What happened? Okay, he's gone again. Okay, let's let's wait for him to revive. Falanka has been asked.
Am I back? Hang on.
Yeah.
What?
Yes.
You're back.
Yes.
You're back.
Am I back? Right. Sorry about that. I believe I was going to say something, but it was just sort of a small comment about the.
Okay. Then I'm just gonna read Falanka's question.
Yeah, that's
he
a good
was so
idea.
kind to repost it for me. He said he has a. Huh?
Can I add a thing with Cepheids and cosmology?
Of course. Sorry.
Right. So Cepheids measure distances to galaxies, and that's how we spotted the universe was expanding. That's all I wanted to say.
Oh, cool. Yeah, people need to know that.
Yeah.
So Falanka has a 200 amp plasma torch at work. The plasma stream runs at, what's it, 35,000 to 40,000 degrees, which unit, centigrade, Kelvin, whatever, I don't know, which is about
that's
5
cool,
times
doesn't
the heat of our sun's surface. I'm gonna keep reading anyway. Question is that it appears purplish, and he has noticed in Elite Dangerous that the color of O-type stars in there was a similar color. Is his plasma torch in effect a miniature representation of an O-type star without the nuclear reaction, or is the color of the light just a coincidence in this case?
I'm not sure I got that. So he's got an L-type star that's very hot. Is that the gist?
O-type, not L-type.
O-type. Okay.
If you didn't understand something I said because I was mumbling, the question is in the radio chatter channel,
Oh wait, I think
along with the picture that shows the color of the torch.
Oh, right.
I believe the question is that his plasma torch appears a purplish color, and coincidentally, it looks similar to O-type stars. And so, is that color the result of similar processes or not?
The short answer is no. Because a plasma torch doesn't emit light by the same principle that an O-type star does. And a plasma stream is a black body, but it still contains traces of whichever elements you're using to produce that flame. I don't know exactly what process plasma torch this is. You can probably look it up. But usually purple colors in plasma torches are because there is some nitrogen involved, or some phosphorus or something like that, which gives it its color. While stars in general don't shine the color they do because of any specific element. It is purely a black body due to their heat and no other effect. While in plasma streams, it kind of gets corrupted depending on what exactly is used to produce it. In theory, if you could heat something using the plasma torch, like a bit of metal, if you heat metal to that temperature, it would look more and more like a black body. But on Earth, it's very hard to get that process to be as perfect as a star. You have to use specialist equipment that doesn't contaminate the color by the specific process of production. Yeah, it's mostly nitrogen. Nitrogen is purple. Nitrogen is a metal that burns purple when you heat it up. And that's not because of...
It's a metal.
And,
Metal?
okay, so
Hang on.
to astronomers, everything is a metal apart from hydrogen and helium. Sorry, I'm getting my job,
Okay.
get me here.
So
Everything
yeah, and since
Okay,
hydrogen
fair
has
enough.
been also been found to have a metallic state in a enough pressure environment.
So nitrogen in this
Oh,
case, the color you're
I was still stuck on
No.
the purple.
is
I was just like, oh, let's do this.
This purple.
Let's light
so
up all the
this
nitrogen
purple-
in the galaxy and fucking
Dang.
purpleize it all.
You can. I mean, why not?
Yeah, let the galaxy burn, or at least the bubble.
Okay, there's two interesting things here. So the purple color you get from heating up nitrogen is not because of its temperature, it's because of a specific electronic transition. So there's two ways that matter can emit light. There's basically only two ways. It emits lights of all colors when you heat it up, and it emits very specific frequencies if you heat up a very pure material. So the LCD screen that you're looking at right now, that has pixels of very specific colors. Now they shine those colors not because of their temperature, it's because they're made to be the specific colors by very precise quantum mechanical transitions that force only one color. And the
Okay,
natural
so,
color, yeah, right.
I need to interrupt you there. You
Yeah,
were
sorry.
saying LCD screens, but LCD screens use a crystal that
Like
polarizes
crystal
light the right
display.
way, so it only lets through a certain frequency. But what you were talking about are LEDs.
It's still related. It's still ultimately you're forcing your atom to only emit one color. So in
Yeah,
LCD
LED screens
yeah.
don't do that. Only LED screens just emit white lights in their backlights, and then it gets filtered.
it gets filtered, but the filter is still conditioned to only absorb some using reflecting
okay.
effect. So it's
Okay,
still not
yeah.
due to temperature. That's the only distinction.
It's the same
Star
principle,
color
just different
is-
applications and different engineering.
Yeah. So star color is temperature. Every other color is due to specific transitions that processors prefer, even if they're not heated up.
Quantum energy states.
Exactly. Quantum processing.
That's my field.
And the only thing is that the other thing is that the color purple doesn't really exist.
Whoa, whoa,
Similar
whoa, whoa! Wait,
thing.
whoa,
That's
whoa,
true
whoa! Like,
also.
whoa! No, back the truck up! Whoa! Let's back every. No, 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 no,
Chase
no!
words on-
No,
in
no,
shadow.
no, no, no! No, no, no! No! You take that back! You take that back! You blasphemer!
This is a joke.
You,
don't get.
you unsay what you just said! Blasphemy!
I love how strong the reaction is. I wonder how
Yeah,
many people
I actually have
know
to turn
this.
down Chang's volume.
I still don't get the joke.
It wasn't a joke.
True. It's true. It's actually a trick. So let's try. I'm going to try to explain it as clearly as I can, right? Your eye.
Oh no!
Right.
Oh no!
Chang,
Okay.
deal with this.
Deep
Uh,
breaths.
I love this.
Get with
Okay.
me.
My body is ready, but there's gonna be some. There are
Tears.
gonna be comments on Twitter. Oh, it's gonna happen.
Okay, so your eyes.
I know you like
basically-
movies, but you can handle the truth.
Your eyes work by having 3 color detectors. So your eyes have 3 little cones in them. Each of them picks up one specific color of light. There's red, green, and blue. I'm simplifying things here, right? So say a photon is traveling through the air and it's green. It has a frequency which is green. It hits your eye. Now only the middle detector that's tuned to green is going to trigger. So your eye will get a signal which is nothing and something in the middle detector and nothing in the blue one. So it goes 0, 1, 0. And then your brain says that combination is green. And in that case, it's correct. Everything's fine. So now let's say a yellow photon comes in. Now a yellow photon has a wavelength in between green and red. So it's going to hit you. It's going to trigger both the red and the green, which are next to each other. And it's not going to hit the blue. So you get a signal 110, and your brain goes, I guess that's yellow. So that's fine. So your brain is receiving one color, specific wavelength, and you can tell what it is. Now the problem with purple is that it goes 101. It hits the 2 detectors for red and blue, but somehow missing the big one in the middle, which is green. Now that can't happen. There is no frequency of light that represents pink or purple. There's just no way to hit these 2 while missing the central one, right? So it can only happen if you're actually getting 1 red and 1 blue, but that's not a photon of the color purple. That doesn't exist. Your brain just goes 101, I'm going to call that purple. Great. But it's not an actual frequency of light. It's a
So it's
color
2
that doesn't
frequencies.
really exist. Yeah. It's 2 frequencies combined.
So what?
It's actually
Well,
how
that's better than a single frequency.
So how I'm hearing what you're saying is that those of us who can see my HUD and see purple, we are superhuman, and we are superior beings to everyone else.
So
No, it means your brain is tricking you and you're not realizing.
No, don't tell me that.
There is no such thing as a purple photon.
So could you, in theory, could you train your brain to see red and blue as distinct colors?
I
No.
guess. I mean, I guess
So-
it's learned on a pretty basic level, but
Honestly,
color perception is
guys,
weird. It's a
I'm
whole
gonna
different
tell you
subject.
all a secret.
Color perception is
I'm gonna tell you all-
neurochemistry. You cannot change your own neurochemistry by using your neurochemistry.
I'm
keep interrupting Chang.
gonna tell you guys a secret, and this is the last time you're ever gonna hear it. The first and only time. I know it's a trick, and that's why I love the color.
Whoa,
Oh, mind blown!
that's amazing.
That's literally
Okay,
why it's my
but-
favorite color. It's my favorite color because it's
So-
a color that doesn't exist.
While we are at well, I beg to differ. While we're at the topic of colors in space, I like to mention the fact that green isn't a color in space that exists at all. That's
You don't see green
What are you
stars. That's
talking
true.
about?
all black
you're
body
talking about
radiation can't
the-
be green.
Right.
That is true. It's more that your brain would never perceive it as green.
So the case I'm making is green is above purple. Just so you guys know out there, green is
No,
less-
don't say that because
We need more
Nagi will
green
hold that
space.
over me. Nagi will hold that over me because Nagi runs with a green HUD, and he will.
He's
Hey,
using
I
a
run
four-card
with
HUD.
green and pink.
The HUD
So I'm above all
Nagi's
of you.
using is not green. The HUD I am using is green.
Mine too. Welcome to the club. Also my favorite color.
Club green.
Yay.
We need more green in space. Okay, but that's as far as we're gonna stray from science. Are there any more real questions for our dear doctor? Because yeah, we've been filling space already.
Well, we're reaching the end. It's okay.
Yeah, that too. But still,
I just got the fun.
We want to give everybody a chance to ask something, if there's still a question. Green is white. Yes, green is white. The spectrum that stars emit, where green actually should be appearing is white.
Well, it's also because our eyes are not very sensitive in that region. Technically, stars can still have a peak frequency of green, except you wouldn't really see it that way.
Our eyes can see
Okay.
the most.
That's
Our
gonna be
eyes
the
can
topic for my
see. Hang on.
doctors.
How am I gonna say this? The color that our eyes can see the most shades of is green. We are most sensitive to green. What have I been told that you've been told differently, or what have I've been told differently that you've been told differently?
Oh, green
What's
is more
going on here?
delicate. So green is a big addition. Is okay. So instead of being just 0 and 1, it's a lot more delicate. So basically, if you see something red in your red detector, it's really 0 or 1. There's red or there's no red, and blue is
Right.
the same. But green gives you all the complexity in between. You can trigger a bit of the green detector and see cyan, or you can trigger a bit of it and see yellow, and all the colors in between. So all the browns, all the shades of orange, all of them involve some amount of green. So actually, our green detector is a lot more, how do you say, finely split, high sample rate, basically.
Yeah.
Oh.
Actually, that's a good way to say it. The sample rate is literally
Yeah, sample rate.
a like
Oh, so technically-
from someone who works in photography and video editing. Sample rate is probably a perfect way of explaining it.
Yeah, true. Also, the fact that well, we've got a limited number of cones in our eyes, so we can only perceive a specific max resolution. So, for example, if you're looking at a 4K monitor right now,
Well, it's not even.
yeah,
It's
you've
not
got more
even. It's
pixels
not
on
even.
the screen than your eyes can
It's
actually
it's not
see.
even resolution. It's literally how much of a color you are capable of recognizing. So sample rate is probably the best term to use for it. Honestly, it literally is.
Yeah, it's the same for screens. And you want to know something really trippy? Some people actually have a fourth detector.
Yes, me, I'm tetrachromat.
No, you're not. Only females can be.
What?
It's on the X chromosome.
then I'm. It's a placebo effect. I'm still.
Oh my God, Michael is a woman. That's why I want to fuck him. Okay.
Whoa. TMI.
Yeah. What? I should shut down. You should think we should finish. No. Yeah. Well. There's no more questions coming in.
Shit got way too real there in the last 10 seconds.
Yeah.
It was a joke, people.
totally
It was
threw me
a
off
joke. I am only. Chank is only interested. Well, no, Chank will do anything, but Chank is mostly interested in hard points. So,
Fun.
It's okay. We always go off topic towards the end of the show. So
Yeah. Well, we've been digressing a lot today, but it was still a lot of
I
fun.
don't know. I think we've got through more questions than usual.
I've not been counting, so I can't say that.
I've had as much fun as usual. So that's how I
At least as much fun
subjectively
as usual.
quantify it, which is
dude, that
doesn't work, but
when I do a talk show, when I'm in an interview, because I don't get to do dangerous cosmology, and I'm like, I feel bad because I'm like, I want to be here. I have questions and I have things, and Shoba eventually talks about things that I ask about, and I'm like, man, I wish I was there. I'm just not, because I'm in Japan. You know, I have a different time zone. So I do the main interviews and stuff like every third interview or whatever, and it's like I'm a complete bumblefuck. But I wish I was here, and I wish I could do more of this. But I just can't because, you know, my timing and zone. But like,
And being drunk also.
yes, I also can't drink.
Sorry, I had to throw that in there.
But like
No,
to
I
me,
have just got a
to
small
me,
question.
I think this was
Okay.
I think this was solid. I think this nailed that element of hitting the topics that we wanted to discuss. We wanted to talk about star classes. That's literally all this thing started out as. And I think we got a lot of information about, like, more information than I knew before about just really basic, simple star class elements. And then went through all kinds of other stuff about how we see it, how we understand it, but also I think I had a lot of fun. I had a lot of fun with all of it.
Yep, it
Yeah,
was really
good.
enjoyable. Anyway, while we're closing things up here, let me just send a get well message to Nightfall, since he's been absent today, and I don't know really why. He's just told us he was feeling bad. Maybe he's just too lazy, but I am assuming it's not
Well,
that.
As far as I'm aware, it's repeated lack of sleep, which can be really
Yes,
harsh.
I have that
Yeah.
also.
I've been there, so
Yeah, I've been there too. So everyone send him your best wishes. Yeah, and we will end things here. This was a great show. Thank you guys for listening. Thank you, Dr. Bosman, for being here again. Glad to have you back, and hopefully we will have another show next week and the weeks after that. Yeah, if any of the listeners have topics they want to suggest, put them in Dangerous Cosmology in the channel on Discord. And also, otherwise, I still have a few topics at hand we can discuss. Yeah, thank you everyone for listening. This was Dangerous Cosmology on Distant Radio 3305, and we will be ending things here. Say goodbye, everyone.
No.
With your names. No? Okay. Then I will do it. So we were,
bye-bye.
we were Chang Sao Tommy,
Yeah,
Selfish Spy, that Michael, and of
see you.
course,
I'll see you when I see you.
yeah, this was that Michael, and of course, Dr. Sarah Bosman, the main star of the show. Have a good night, everyone, and see you on Friday with our regular weekly interviews. Bye bye.
Bye.
Bye bye.